So in the previous class we have seen means uh, whether null subspace and null space and the linear combinations. Okay, so in the previous problem, so as the number of variables in matrix, that is 4, but the v vector means which we call as b, so that has 3 entries. Okay, since null is subspace of R4 but the variables in v is 3, so because of that reason, okay, so it is not possible, means we couldn't possible be in the null. Okay, so after that, so we'll move to the linear independence. Okay, so linear independence means it is basically the trivial solution and the non-trivial solution, so it's like that. So means here, if there are set of vectors v1 to vp in Rn, means in Rn field, real field, it's said to be linearly independent. Okay, the system is said to be linearly independent if the vector equation, okay, so already we have seen that x1 v1 plus x2 v2 plus up to xp vp is equal to 0 if it has only trivial solution. Means if after applying row reduced form or row operations, so if all the values x1 x2 x3 up to xp are 0, if all the values are 0, then we call as independent. Okay, suppose the set of vectors is said to be linearly dependent if there exist weights, means 7 to p, not all 0, means if some of are 0. Okay, if the weights not all 0, okay, such that c1 v1 is equal to 0. Okay, means it's the same thing like earlier, means not all the values of x1 x2 x2 are 0, if only some of the values are 0. Okay, in that case we call as that is a dependent. Okay, so here let us take an example and we will come to know. So here we have three factors v1 v2 and v3. So determine v1 v2 v3, is it linear independent? Okay, and if second one, if possible find a linear dependence relation between v1 v2 and v3. First we need to find whether is it linear independent or not. Next, the relation between v1 v2 and v3. So here, so v1 v2 v3, so as we are seeing here, so this represent in the matrix, so like v1 v2 v3. Okay, so b element, okay, so augmented matrix, so we have taken b as 0 here. Okay, so you've taken b as 0. Okay, so your vector equation we have taken x1 xp is equal to 0 here. Okay, let us move. Okay, b has taken as 0, x equal to b is 0 here, so b has not given. So augmented matrix, so this is a and this is the b what we have added here. Okay, just we need to go on the row reduction, means the row operations we need to apply. So after applying all these things, so we are getting the equations like this. Okay, means lower triangle is 0 and here diagonals 1 minus 1 0, like that. Okay, so if you see the equations here, x1 minus x2 x3 is equal to 0 and minus x2 minus x3 is equal to 0 and x3 is equal to 0 here. Okay, so if you see this here, all the x1 x2 x3 are not 0, means for example only x3 is here. By looking at these equations, these three equations, only we are seeing x3 as a 0, not other things. Okay, so not other things, it is in the form of zeros. Okay, okay, other things are not zeros, so because of that the system we call as linearly dependent. Okay, so if you have all the zeros, okay, if you have all the values as 0, then we can call as the system is independent. Okay, so you'll see some more the problems on this. Okay, so here let us take one more, means okay, one more thing. After getting this, we need to find out in the B section the relation between v1, v2 and v3. Okay, here what we can say is, so as I told earlier, only x3 is 0 here, so that we call as the free variable, and other we call as basic variable. So if there is a free variable, okay, as we can say is both are 0, free variable we can choose the values. Okay, we can choose the values. You can see here, so if x3 is 1, if x3 is 1, then x2 is -1 and x1 is x2. Okay, so that's why I told, so these two are not zeros. Okay, so we need to assume the x3 value and we need to calculate other values. So equation you can give like this. Okay, so the system is linearly dependent. Okay, so take the next problem. So determine if the columns of the matrix are linearly independent. Whether is it linearly independent, the columns of A. So similarly here, so what we need to do here, A is given, so 0 we need to take with augmented matrix. So B is not there, we need to take 0 as augmented matrix. Then again so as the first row is non-zero, you can see the first row is non-zero, we need to exchange such that the first row, top row, should be non-zero. Okay, so then we have exchanged r1 and r2, and again we need to nullify so these values, the pivot columns. So we are doing row operations such that lower triangle should be 0. Okay, by seeing this, okay, by seeing this we can say that there is a solution. Okay, so there are three variables. Okay, that means there are no free variables here. Okay, so we have the definite the solution for this. Okay, here okay, definite solution, and here we can see here by making some more means some more row operations. Okay, so as I mentioned here, for doing further row operations we can get this result, means the fully the row echelon row reduced echelon form. Okay, in that case all the three are 0, x1, x2, x3, means upper values also we got it at 0. So after doing the row operations, okay, then we can say that the matrix is the linearly independent because all the variables x1, x2, x3 are 0. Okay, so now there are some important points to remember while doing the problems. Okay, so if set contains the vectors, okay, if set contains the vectors, if set contains the vectors, then there are entries in each vector. The set contains vector, okay, so there is small mistake there. The set contains vector, okay, if some contains number of vectors, there are entries in each vector. Okay, then set is linearly dependent. Okay, that is v1 to pp in R is dependent if p is greater than n. Okay, p is nothing but if the number of elements in the vector, okay, if the number of elements in the vector means the whatever v1, v2, so what we are calling, okay, if these number of these, okay, any set in Rn, if it is greater than n, okay, so whatever in each vector, okay, means the meaning of this is one is the number of vectors, okay, number of vectors, okay, and that is if it is greater than n, okay, n is that is number of variables in the vector. Okay, so if it is p is greater than n, then we can call as a linearly dependent. Okay, so all these things means these points will see in the problems also. Okay, we'll see in the problems and you will come to know how exactly this relation, by saying this relation we can call as linearly independent, all those things. Okay, so there is, okay, if means this is n is number of the variables. Okay, so here p is if p is greater than n, then we call as linearly dependent. Okay, suppose if there is a set v, okay, in Rn contains the 0 vector. Okay, if one of the this one contains the 0 vector, then linearly dependent. Okay, here we can show here. Okay, so if v1 equal to 0, so shows the s is linearly dependent. Okay, we can say if one of the vector is like this 0 vector, okay, there is v1 v2 v3, so many vectors will be there. Okay, in one vector number of elements is this one n. Okay, so here, so if the one of the vector is 0, then we call as linearly dependent. Similarly, if the determinant of the reduced or augmented matrix is non-zero, okay, so we can calculate the determinants also. If the determinant of the matrix is non-zero, then we call as linearly independent. Okay, similarly, if the determinant is 0, we call as linearly independent. Means, okay, so here one more is there. If the two vectors lie on the same line, okay, how we can know that the two vectors lie on the same line? We can see the values here, 1 by 2 and 2 by 4. It is nothing but 1 by 2 only, just it is scalable by 2. Okay, so here similarly here 1 by 2 and 3 by 6. Okay, it is scalable by 3. So if it is like this, then it is linearly dependent. Okay, so why we need to look all these things is, so while solving the problems, if p is greater than n, directly we can say that linearly independent. And if we know, if you can calculate the determinant very easily, then we can say that linearly independent if the determinant is non-zero. Similarly, if one of the vectors is 0, then we can say that linearly dependent. Okay, and if the values are like this, means 1 by 2, 2 by 4 and 4 by 8, so like that, okay, then we can say that linearly dependent. Okay, so these are some of the hints or important points, so while solving we need to keep in mind. Okay, so here, so let us take the problems. So find whether the set x square minus 1 x plus 1 x minus 1 is linearly independent. Okay, set whether is it linearly independent in the vector space for all polynomials over the real numbers, or the field of real numbers. Okay, so here the three vectors v1 v2 v3, so three vectors are there. Okay, x square means c1 v1 plus c2 v2 c3 v3 0. So where the vectors is v1 v2 v3, so these are the vectors here. v1 is equal to this, like this. Then these are the weights c1 c2 c3. Okay, so if you want to write them in matrix, okay, so anyway it is equal to 0 as b is not there. So what we need to do is, as I told, the three terms here. Okay, one is x square, one is x, one more is constant. Okay, not one, you can take as a constant, x square position, x position, and constant position. Okay, so if you see like this, then if you see the first one, x square is there, no x term and constant term is there, so 1 minus 1. Second term, x position is there, constant is there, no x square is there. Okay, the third term, x position is there, minus 1 is there, no x square term. Okay, so like this we need to write the matrix from the given set of polynomial. So here, after writing here and apply row reduced means operation, and by doing this we are getting upper triangle, lower triangle as 0. Okay, so here by seeing this, it is clear that means c1 c2 c3 are 0. Okay, means here these elements are 0, and even if you do the minus 1, that will also become the 1 here. Okay, by doing one more row operation. Okay, so here the linearly independent. Okay, even you can say that if you calculate determinant. Okay, so if you calculate the determinant, so determinant is not 0. Okay, if you calculate here, so that is minus 2 minus 0, so minus 2 is the determinant. Okay, we will not go detail how to calculate the determinant here. So for this matrix, if you calculate determinant, it will not be 0, so directly you can say that linearly independent. Means what I can say is, so after applying all these row operations and coming to some stage, if you calculate the determinant, so directly we can say here. Okay, so that's also possible. Or we can go to at the end, lower matrix and upper matrix, you can make it 0. So all the possible things are there. The next problem, so here, determine following set of vectors to, so this is in terms of the matrices, so this is in terms of the polynomial equation here. Okay, so matrices, so as I said, okay, so this is 0 matrix, so whatever the matrix, first we need to write in equation. Okay, means we need to write in equation. So first term 2 3 1, 2 2 3 1, second one is only c1 is there. Okay, no other, here 0, here 0. Okay, the third one 0 2 2. Okay, first term is not there, only c2 term is there, c3 term is there. The fourth one 1 and 1. Okay, here it is 1 and here it is 1, so c1 plus c2, so c3 is 0 here. Okay, the same thing if you write in equation by matching with this, so this one and this one, c1 0 and this third term, fourth term. So if you draw this properly, so then directly we can map into the matrix here. Okay, so we need to map the matrix here. So after that you apply row operations. Okay, so now after getting here, so after getting all these operations, so now no need to reduce further, because so determinant, if you see again here, okay, so if you see the determination, sorry, is determinant. Okay, so determinant of the matrix is not 0. Okay, determinant of the matrix not 0, so directly you can say that linearly independent. So because of this reason I told to remember, means the 4 whatever the conditions or points hints, so that we can if you follow that properly, then we can say that they're linearly independent. Otherwise even we can go for further reduction and see that whether all the values are getting 0 or not, means the variables. Okay, so here, okay, okay, independence involves null space, means why we are calling as null space, because we are taking as 0 here, means x equal to 0. So that is nothing but this is all x1 x2 x3 is equal to 0. Okay, or c1 c2 c3, means anything. In some places you have taken as x1, in some places you have taken as v1 c1 and all those things. Okay, so let us go for the next problem. Then basis and dimensions. So what are the, what we call as basis and dimension? So here let V be a vector space on the over the field F. The subset B we called, the subset of V called as a basis of V. Okay, there is a subset, if means there is a vector space V, in that we call B as a subset. If you are calling as B as a subset, and this subset we are calling as basis of V, we are calling as basis of V if it have the properties like 2, means the first one is linearly independent, the second one B spans V. Okay, B spans V means it should be have the means the linear combination of which consists in the vector space. Okay, then what is a dimension? So dimension is nothing but, okay, dimension of the finite dimensional vector space V over the field F is the number of elements in the basis. Number of elements in the basis means here we call, after doing linearly independent and after showing that B spans V, we have the elements in the basis. Okay, whatever basis we are calculating, we have the elements in that. The number of elements we are calling as a dimension here. Okay, so that will see in the problems. Okay, so here if there is some problems, okay, suppose if r is equal to e1 e2 e3, so like that en. So if in that case, if you want to take the standard values means you will take like this, in if the problem is like this. Okay, e1 is equal to 1 all 0, e2 is equal to 0 1 all 0, it's like identity matrix only. Next En is equal to the last one. Similarly, if you want to take the matrix, okay, if you want to take matrix, then we will take as, okay, it's actually the first one, actually this value should be 0 here. Okay, so 1 0 0 0, all other terms are 0. Okay, next 1, all other terms are 0. Next 1, all other terms are 0. 1, all other terms are 0. Just it is the same thing representing in a matrix form. Okay, similarly, if you take uh, the equations polynomial, then it is 1 comma x comma x square comma x cube. So like that it will go on. Okay, so let us take some more problems on basis and dimensions. So determine whether the set of vectors, okay, is a basis of R3. So as I told, n is nothing but number of vectors here. Okay, sorry, number of elements in vectors. Okay, so in each vector we have 3 elements, so because of that n is 3 here. Okay, so in any case, again we need to follow the same row operations or row reduced method. So write the vectors as matrices, okay, and add the augmented matrix as, means with 0. Okay, apply row operations. So after doing this, you can see that the third variable is, means, sorry, the third variable is 0 here. Okay, third variable is the free variable. Okay, and also the determinant of the matrix. So if you see here, the determinant of the matrix is 0. So we can say that the linearly dependent. If the matrix, if the determinant of the matrix is non-zero, we call as independent. So as the determinant of the matrix is 0, we call as linearly dependent. Okay, so first property only for the basis. Okay, if you want to show as a basis, what is the first property? First, it should be linearly independent. Okay, first, that is only it is failing now, it is linearly dependent, so no need to go for finding the basis. Okay, if it is linearly independent, then you find the basis, but here it is linearly dependent, so no need to find out the basis here. So directly we can say that set of factors is not basis of R3. Okay, so let us take some more example. Next example. So here we have another 3 factors with 3 elements. Okay, so here the first property, means the 0 we need to take, add augmented matrix, do the row operations. So here the determinant is non-zero, so we can say that these all c1 c2 c3 are 0. So because of that we can say that they linearly independent. Okay, so means determinant is fine when we are, means square matrix, means m and n are both are equal, then the directly we can say, means directly we can see the determinant. Okay, otherwise we can apply row reduced format as said earlier. Okay, so now the second property, whether we need to find out the basis. Okay, so now what we need to do is basis in the sense, so earlier we have taken as 0. Okay, b as a 0. So now to find the basis, we need to take some unknown values, means b as, for example, b1 b2 b3 we need to take. So again, so whatever the row reduced form, whatever we got in the first, so directly we can use that one. Okay, use that. Okay, you use that and equate to the whatever, means here equate in the sense, what we need to do is from the starting itself we need to consider b1 b2 b3. So here whatever the row operations what we did here, okay, it will apply to b also. Okay, we can see here first it is as it is b1 b2 b3 is there. Okay, b1 b2 b3. So as we apply the row operations like this one, r2 minus r1. Okay, r2 minus r1 means it will become b2 minus b1. Again next one, r3 plus r2 means, okay, r3 plus r2. Okay, this one, so already r2 is b2 minus b1, so plus means this third row will become b3 plus b2 minus b1. Okay, the same thing applied to that also. So then what we need to do is, okay, so then equate that, means 2c3 is equal to b3 plus b2 minus 1. Okay, this is the c3 value. Then minus c2 plus c3 is equal to b2 minus b1, so that will lead to c2 is equal to this. Then c1 plus c2 is equal to b1. Okay, then so already we know values of c2. Okay, so we can fill here the c2 value. Okay, and we can find out the c1, means basically by equating, okay, that these equations to the whatever b term, and we need to find out c1, c2, c3. Okay, so here given vectors can be expressed, means we are expressing properly here. Okay, we are expressing properly the b term in terms of the, means whatever the variables are there. Okay, given vectors can be expressed as linear combinations, so S is a basis of v3. Okay, S is basis of v3. Similarly, we will take other example. So determine whether the set S forms the basis of R3 and find dimension. So till now dimension we have not seen. Okay, so dimension also we need to see. So here the same problem. First we need to take the 0 b as 0 and apply row reduced form, and here determinant of matrix is again here not 0, so it is linearly independent. So we can go, so linearly independent. Okay, here we no need to find out the basis, he has asked for dimension. Okay, so what is the dimension here? So number of, we can say here at this place, number of non-zero row entries. So non-zero row entries, so which are the non-zero row entries, how many are there? So 1 2 3, all are non-zero. Okay, so we can say that dimension is 3. So even you find out the number of bases further by considering this 0 vector as b1 b2 b3. So then if the bases are 3, then we can call as that also dimension of 3. Okay, then you take determine, next problem, determine the basis of subspace spanned by these 4 vectors. Okay, so now here the 4 vectors are there, so here they have taken as a b c d. Okay, the same thing we can, so now here how to write in the matrix form. Okay, so here if there are 4 vectors here, so you can see 1 1 2 1, so 1 1 2 1, then minus 5 1, okay, then the minus 5 1 minus 4 minus 7, you can see here this term minus 5 1 minus 4 7, and the third one third row, and the fourth one the fourth column. So some, means the order should be there. Okay, this whatever the row, the first elements we have taken as vertical here, the second element we have taken a second column as a column. Okay, so after writing this in a proper order, then again apply the row operations. Okay, so after applying the row operations as mentioned, so here we can see after applying here, so we will got the matrix like this. So here all the values, okay, because here c3 and c4, okay, here c4, okay, c3 and c4 are the free variables. Okay, because of that this all the values are not 0, so because of that we can say that linearly dependent. Okay, so if it is linearly dependent, so S is not a basis. Okay, then what is the dimension here? Non-zero rows are 2. Okay, non-zero rows are 2, so then we can say that dimension is 2. Okay. So the next one, take the next problem. So here we have again 1 2 3 4 vectors. Okay, the 4 vectors v1 v2 v3 we have taken. Okay, the 4 vectors, but the number of elements is 3. Okay, so like earlier what I am talking about p and n, so p is nothing but number of vectors. Okay, that is v1, v2, v3 up to vp. Number of vectors is 4. So what about n? Number of variables in the vector, in one vector, is n is equal to 3. So n is equal to 3 and p is equal to 4. So we have see that we told that if p is greater than, if p is greater than n, then system is linearly dependent. Okay, so as I said here, if number of unknowns is less than number of equations, okay, or if p is greater than n, the linearly dependent. Okay, so this is how uh, we can verify p is greater than n. Okay, so here again, whatever it may be, so first we need to, means directly we can't say, we need to do the row operations. We have written in the matrix form and applied the row operations here. Okay, and here we can see, okay, the third, the variable, okay, that is the free variable here. So even this, by this we can say that linear dependent, and already we told that p is greater than n, that also we can say that linearly dependent. Okay, so now dimension is 2, that is non-zero, rows is 2, and also the dimension, sorry, basis. So basis, what we can call is means the further, means the row reduced is over, the further we can't reduce. So here this is 2 rows are left, so 2 rows, so these we call as a basis, the basis of the vector. Okay, last, after doing all these row reduced sorry, row operations, what are the final non rows will be placed remaining, so that we call as a basis now. So number of bases is nothing but the dimension of the vector. Okay, so again, the one more vector, one more problem, find the basis of row space of a. Okay, so row space of, we need to find out the basis of row space of a. Okay, so here there are how many rows? 1 2 2 3 4 5 rows are there. Okay, so write in matrix and apply the row operations. Okay, apply row operations, and finally we are getting out of 4. Okay, one second. Okay, so after applying all these operations, so we will get, okay, we are getting the values, means the vector like this. Okay, so then how many number of non-zeros? Okay, how many number of non-zero rows? 3. So these 3 we call as a basis. Okay, so that is this, they are calling as name as w, w1, w2, w3. So these rows we call as a the basis. Okay, so basically in all the problems we need to apply row operations. Okay, finally we need to, in some of the problems we need to find out determinant, and we say that linearly dependent and independent and dependent. And if you find out only basis, means we need to go for at the last. Okay, means finally to get the how many non-zeros are there. Okay, after getting that, the whatever the non-zero values, so that will be the basis of the vector. Okay, and here again find the basis. Okay, find the basis of the subspace spanned by the vector, means here again 3 vectors are there. Okay, so we need to find out the basis. Here you can again you write in the matrix form and apply the row operations. Okay, after applying row operations, okay, we can see here, means if you want to find out the dependent and independent, we are taking ax equal to 0, means the 0 b as a 0 we are including in the augmented matrix. Even you can see here the linearly independent we are taking as 0 vector. Okay, but in the basis, you can see here in the basis, while calculating the basis we have not considered the, okay, here whether set of factors is basis. Okay, so directly he has given augmented, one second, So 310. Okay, here we have, okay, so here we have considered the linearly independent or not. Yeah, for getting linearly independent or not, we are considering the 0 here as a B matrix. Okay, and here, okay, to find out the basis we have taken as b1 b2 b3, and here the basis. Okay, so direct we have considered 0, and directly by seeing the determinant we are telling that whether dependent or not dependent. Okay, sorry, and here, okay, here we have directly taken the vectors, and we have seen, first we need to find out linearly dependent or dependent. So depending upon that we can tell that whether is it basis of, if the first property only it is fail, if it is linear dependent means no need to go for further to prove the basis here. Okay, here again we need to find out dimension and basis, the four vectors. Okay, so here one more problem. Okay, so here also, so what we are there, so in this problems we have considered three vectors, and by doing row operations, okay, by doing row operations, so we are telling here the non-zero rows are 2, so these are the bases of subspace of row space of A. Okay, now similarly here, so if they ask basis for column space of the matrix A, okay, if they ask this column space of the matrix A, okay, then we know that means column space of A is equal to row space of A raised to T. Okay, column space of A is equal to row space of A raised to T, means transpose of A matrix. Okay, so now here the matrix A as given here, the column space of A means, suppose if you consider this is a row matrix, then you take a transpose of that. If you take a transpose of that, so it will become a column space. Okay, it will become the column space. So take a transpose matrix, and the same method what we need to apply, the row operations. Okay, and here by doing this we can say here how many non-zero rows are there. So 1 2 3 non-zero rows. Okay, so 3 non-zero rows are there, so those are we call as bases. So first, second and third. Okay, and if you represent in the means the basis of the column space of A, and basis of column space of B is, that is A raised to transpose of matrix. Okay, so these we in terms of columns we can, the same thing we can write in columns. Okay, anything. Okay, so that is so one more method in the sense, refer the previous pivot 10 minutes. Okay, the same thing, just they have made it as what is it, row reduced echelon form. Okay, so to get, they made it 1 1 1 as diagonal. Okay, until that the row operations are carried out. Okay, so here, so what we seen today here, so we have seen linearly independence and linearly depend means how we can say that the system is linearly independent, and how we can say that linearly dependent. Okay, independent means all the values of x1 x2 x3 or weights should be 0. Okay, if any one of the thing is, okay, the free variable in that only one of the vector is 0, others are not 0, then we call as the linearly dependent. And also we can set, or we can say on the basis of determinant. Okay, and also we can say on the basis of the number of vectors and number of variables in the vectors like p and n. Okay, and also we can say that if the values depending upon the vector values we can say. Okay, and after calculating dependent and showing the dependent independent, then we can calculate the basis. Okay, basis and dimension. So dimension is nothing but number of elements in the basis, and basis how we can calculate, after knowing if it is independent, then we can have the instead of 0 we have the b term, and equate whatever the row reduced form into b term, and get the values of the c1 c2 c3. Okay, so this is how linear dependent and independent and basis and dimension. Thank you.